A good TIG weld is generally regarded as the Rolls-Royce among welds. TIG will weld stainless and heat-resistant steel, mild and alloy steels, copper and copper alloys, in fact any weldable metal from titanium through the precious metals to cast iron, and most importantly, aluminium and its alloys, and magnesium and its alloys. Where quality is essential, TIG welds are being specified more and more. For nuclear applications, aero engines and so on, where strength and reliability are vital. So what is TIG? TIG is an arc welding system, but it differs from manual metal arc welding in several basic ways. In the manual metal arc process, the electrode which strikes and holds the arc also serves as a filler rod. It's a consumable electrode. Whereas the electrode in TIG is non-consumable. It's made of tungsten, which has a high melting point, and it serves only to maintain the arc. When needed, a separate filler rod is used, as in gas welding. And here's another great difference. Some of the rods used in gas welding and in manual metal arc welding contain flux to prevent oxidization of the weld metal. The flux produces gases which shield the weld pool from atmospheric oxygen. It also produces a slag which shields the completed weld as it solidifies and cools. But TIG welding uses no flux. Oxygen is kept away by surrounding the weld with a stream of inert gas. This is where the system gets its name. Tungsten electrode, inert gas shield. TIG. Electrodes are of various types according to the job to be done. The handbook tells you about these. The inert gas we've been talking about is sometimes helium, and there are other mixtures with hydrogen as a common additive. Probably most commonly used is argon, and this is the gas we shall feature. A hose brings the argon gas to the torch body, and a ceramic shield directs the gas to the weld pool and adjacent metal. One side of the power supply connects to the electrode and the other to the job in the normal manner. But there's one more thing. In metal arc welding, the arc is struck by touching the job with the consumable electrode. But not in TIG welding, where the electrode would wear away and the tungsten contaminate the weld. In the TIG system, a high-frequency spark is fed to the electrode, allowing the arc to strike without physical contact between electrode and job. This is the basic TIG system. Before seeing how it's used, let's look at an important electrical characteristic of the arc. Let's assume a DC power supply with positive connected to the electrode and negative to the job. When the arc strikes, the flow of electrons is upwards from the job to the electrode. This has one advantage. The upward flow of electrons can lift off into the gas stream any oxide which is tending to collect in the weld pool. But it has two disadvantages. First, the electrode can become so hot from the electron bombardment that it begins to melt despite its high melting point. Here it is in slow motion. The electrode is positive, it's being bombarded by electrons, and so it's overheating. It waves about, making welding control difficult. Finally, it melts completely and contaminates the weld. In fact, with this polarity, of the heat generated, 2/3 is in the electrode and only 1/3 in the workpiece. This produces the second disadvantage, shallow penetration into the parent metal. With the polarity reversed, both of these disadvantages disappear. The job is now bombarded by the electron stream, so it gets hotter. Penetration is deeper and narrower. The job this time takes 2/3 of the heat. The electrode, now taking only 1/3 of the heat, is free from the risk of melting. This is the polarity used for normal DC welding. Negative to the electrode. But with aluminium and magnesium, there's a special problem. In normal atmospheric conditions, these metals coat themselves with a layer of oxide, and this layer has a much higher melting point than the metal itself. So if we try to weld it with negative electrode DC, the metal will melt, but the oxide won't. The oxide forms little sacs, coating the globules of molten metal and preventing them from flowing into a weld pool. This is where we could make use of the positive electrode system, where the electron flow lifts the oxide off the surface. But we know that this has disadvantages. The answer is to use one polarity rapidly followed by the other to compensate. An alternating supply. AC, changing polarity twice for every cycle of mains supply. Negative electrode to bombard the job and break the oxide up. Positive to lift the oxide off. Negative to heat the job. Positive to lift the oxide off. And so on until deep, narrow penetration is achieved. The electrode heats up, of course, on positive half cycles, but cools down again on the negative half cycles. Here's AC welding of aluminium in real life and at normal speed. Notice the clear and tranquil weld pool, completely free of that oxide that can be seen retreating in front of the arc. So the rule is TIG DC with a negative electrode for steels, ferrous alloys, copper, cast iron, platinum and brass. TIG AC for aluminium, magnesium and their alloys. So much for the theory. Now let's look at a demonstration weld on 3.2mm stainless steel. TIG welding power sources come in a variety of types. This is a combination set which supplies all the services to the torch for DC and AC welding. For stainless steel, of course, we need DC. The air-cooled torch we'll be using here gets its gas and electric power from just one socket. In part 2, we'll see the extra connections needed for a water-cooled torch. Then there's the on-off switch connection for the hand switch on the torch, or for a foot switch if you prefer. Finally, there's the positive return cable to be connected to the workbench and therefore to the job. Negative electrode, remember. To assemble the torch, fit a ceramic nozzle. Grind the electrode to a fine point. The electrode size in this case is 2.4mm. These sizes are in the handbook. Fit the electrode to the collet and insert them into the torch from the back. Fit the electrode cap and before tightening it, adjust the electrode stick out to 5mm. The torch is ready. Now for the rest. Turn on the argon. Switch on the power and set the welding current. Set the gas cutoff delay. More about this later. And finally, set the flow rate of the argon, 5 litres a minute in this case. Safety equipment consists of high-resistance overalls, gloves, and a head screen fitted with an EW11 filter lens. Before starting, all the edges to be welded should be cleaned with a solvent. And the same for the filler rod. Then a clean snip at one end and a hook at the other to protect the eyes of passers-by. Well, with all preparations complete, we can get down to the welding. First, you'll need tack welds to hold the plates in position during the main weld run. Hold the torch about 3 millimeters from the job, strike the arc by switching on, form a weld pool, and feed in enough filler to form the tack weld. The welds should be at 75 millimeter intervals along the join. When you switch off, the gas continues to flow for a while to protect the weld as it solidifies and cools. This is the cut-off delay, which was set earlier. 10 seconds in this case. Now for the main weld. 3 millimeters from the job again, and strike the arc. Melt the first tack weld to form a weld pool, and feed in the rod. The torch should be 80 degrees from the horizontal, and the filler rod at right angles to the torch. Move in the direction of the filler rod at a speed which maintains a uniform weld pool. Too slow and the weld pool will grow. Too fast and it will shrink. Keep going at the same steady pace, remelting each tack weld as you come to it. At the end, hold the torch in position to protect the cooling weld until the gas cuts off automatically. That's the first run, which must now be cleaned before the second. And the second run is done in exactly the same way as the first. This has been DC welding of stainless steel. In part 2, we'll look at AC welding of aluminium.